to this video on writing equations given the slope and any point, and this is specifically going to focus on slope-intercept form, though we will address other ways to do this in future lessons. Want to say it at the beginning, please like this video if you find it helpful and subscribe to the channel for more math content. Drop a comment below and let me know what you think. This is what we already know. So we've already done some talking about writing equations of lines and why that's a thing, why this is a skill that we want to develop. And what we already know is that to write the equation of a line, we need to know how steep the line is, that is the slope, and where it is located on the coordinate plane, point. If we have those two pieces of information, then we know that there is only one line that will meet both of those qualifications. So one line that goes through a point. Okay, so if we have our coordinate plane, now if I pick a point, there's actually an infinite number of lines that go through that point, but there is only one line that goes through that point and also has a given steepness or given slope to it. So the moment you say this is how steep the line needs to be, you've gone from infinite number of lines down to one. Now, once you have this information, and the information might be given to you, or the information might be something you have to get from other information that you're given. But once you have the slope and a location, there are two main strategies people use to get the equation. The first is what we're going to look at in this lesson, which is to use slope-intercept form. The other very popular strategy is something called point-slope form, and we're going to save that for a future lesson, and we'll kind of go through where that comes from and when you would want to use that strategy. So why use slope-intercept form? What are some of the advantages to this? And I've done this different ways in my own classroom. I know I've talked to my colleagues about it, and we don't always do the same thing every year, but there are some really, really great reasons for why we want to use this form. One of them is that most students are familiar and comfortable with this form. In other words, it's one less thing to memorize. If you have already learned slope-intercept form of a line and you've been using it and you've gotten good at interpreting what the slope is and what the y-intercept is, then why not stick with the thing that you know? Why bother incorporating some other form of a line that's like another thing that you have to memorize? And so a lot of times this is a great way to do it because you as a student are more likely to remember this form of a line and therefore the strategy used to write the equation. The other great reason is that it's easy to graph and gives us key information about the problem without having to do more steps. So in application problems specifically, the slope and the y-intercept usually represent something. And when we have it in slope-intercept form, we're able to pull that information right off of it. If we right off of the equation, if we use other strategies or other forms, we have to take those forms and kind of juggle them around a little bit before we can get that information. So it might have a few more steps in the process here, but can save us some steps later. So here's the key idea to remember, like before we launch into it, because I could just go in and say, here are the steps, just mimic what I do. But the reason this strategy works is because of these underlying ideas in math, like why do these steps work? And the better you understand those ideas, the more likely you are to remember how this strategy works and employ similar strategies without necessarily having a teacher teach them to you. So here's the key idea. Any point on the line makes the equation true, okay? If you've been following these videos, you know that when we first did like graphs of lines or solving equations, I really, really emphasized these ideas, and now we're going to employ those ideas. So consider the equation y equals 2x minus 1, and we have the graph of that equation over to the right. If I pick any point on that line, it will make the equation true. So I won't belabor this too long, but I do want to emphasize the point. So this is the point 4, 7. So we've got the point 4, 7. In other words, x is equal to 4, y is equal to 7. If I take those values and plug them in, so y is 7, and 2 is 4, and we carry out order of operations. 2 times 4 is 8, and 8 minus 1 is 7. You will notice that that is true. And I could pick, we'll pick a number down here. So this looks like -2, -5. And once again, we have the x and the y. And then I write an m. Do better than that. This is 2x minus 1. So we'll have -5 equals 2 times -2 minus 1. 2 times -2 is -4. And -4, now it might help you. I do this a lot in my videos. Instead of saying -1, to say plus negative. Okay, to change that over there so that you don't end up like bouncing back to like a -3. I've seen tons and tons of students do that. So -4 plus -1 gives us -5, and that is true. And this would also work for, say, decimals. So if I were to come over here and look at, say, 1.5, it appears like that is a 2. So 1.5, 2. So we don't typically use non-integers because why would we? So 2 times 1.5. 2 times 1.5 is 3, and 3 minus 1 is 2. So it's not just the lattice points, although we do tend to pick lattice points for obvious reasons. Any point on that line, and there doesn't have to be a dot there, just any point on the line. If you pick that point and plug it into the equation, it will make the equation true. Now, the reason why this is such a key idea is because in this strategy, we're going to be given the slope and a point. And we're going to use the x and the y values in that point to help us figure out what the y-intercept is. So let's go on to an example, and I'll show you what I mean. So write the equation of the line with a slope of 3 and going through the point 6,5. Now, just to really drive home the point, I want to make it really clear that there is... Okay, that there is only one line that meets this requirement. So it goes through the point 6,5. So 1, 2, 3, 4, 5, 6, and then up 5 is like somewhere here. Okay, and then the slope is 3. So my rise over my run means I'm going to go up 3 over 1. And there is only one point that does that. Now, something, again, that my students will often like forget that they could do is if you 100% blank out on everything that I am about to show you, but you've got some graph paper, you can probably do that and count the slope all the way back to finding wherever the y-intercept is, which is going to be down here somewhere. Okay, this is a super rough sketch. And so sometimes you can go about this like through the back door, but it requires a fluency between the graph and the equation and knowing what these words mean and saying, well, if I can't remember one way, I'll figure it out another way. Now, here's how the strategy works. In order to write the equation of a line, you need to know the slope, which we have been told is 3. Now, in our slope-intercept form, we need to know the slope and we need to know the y-intercept. So we'll need to plug in a number here for the slope and a number over here for the y-intercept. The problem is I don't have that number. I've got this piece of information instead. So what we're going to do is we are going to borrow an x and a y. So I have x is equal to 6 and y is equal to 5. Now we're going to consider those like loaner points. All right, I tell my students we're going to borrow the x and the y because I know that any point on that line, if I plug it into the y equals mx plus b, it'll make the equation true. So here's how it looks. We're going to plug in a 5 for the y. We're going to plug in the 3 for the slope. We're going to plug in 6 for x. And then what that means is that the only thing in this equation that I don't actually have a value for is the y-intercept. But because I know that the point 6,5 would make this equation true, I can go and use that to figure out what b is. So 3 times 6 is 18. And then we would subtract 18 from both sides or add -18. On my left, I have 5 minus 18, which would give me -13. 18 minus 18 is 0. And now I have a value for b. So now if you look at this, we have a value for m and we have a value for b, which means that we are green lighted for writing the equation of a line. So remember, we were just borrowing the 6 and the 5. We're not keeping it. We're just like, we were borrowing it in order to find b. Now we're going to put those back, and all we need to do is plug in the values for our m and our b. So we'll have 3x minus 13. And if I had graphed it, okay, if we come back and look over here, negative 13 is probably a reasonable value for the y-intercept, keeping in mind that this is an extremely rough sketch where I have not equally spread things out, and I was just guessing about the rise over the run right there. So that I know that that's a reasonable answer. And any other point that we were find, so like the 6, 5, but any other point that we could find on that line, we could plug into that equation. It would also make it true. And that's pretty much how the strategy works. So there's our first example. Now, you might see what I call yucky numbers. I put that in quotation marks. That's not a technical math term, just yucky numbers. That means numbers that don't come out super nice. So we have write the equation of the line containing. Now, something else I'm doing in this lesson without really saying it explicitly, although I guess I am now, is I keep changing up the phrasing for this. So the last problem said going through the point. This one says the line containing the point. Those are all different ways of saying that this point is on the line. Okay, so just a heads up. In fact, somebody could say that, where the point is 0.5, negative 2 is on the line, passing through the point or going through the point, containing the point. Like they're just all ways of saying, hey, this point is on the graph. So here we've got a slope of -1/2. And we're given this point 5, negative 2. And so what we're going to do is borrow the x and the y out of that, so that we can figure out where the y-intercept is. So in this case, y is -2. My slope is -1/2. My x value is 5. And this is where you might get hung up with some of the arithmetic. So I'm going to just do some scratch work over here. -1/2 times 5. Okay, so 5 as a fraction would be 5/1. So we could just multiply those straight across and we would get -5/2. So right here, we have -5/2 plus b. Now, just because that's a fraction does not change any of your algebra. And my students will often hear me say that you want to separate your algebra from your arithmetic. Sometimes students can have some glitches with their arithmetic, say adding and subtracting fractions, when really their algebra is fine, but they'll think, oh, I'm so bad at algebra. And no, your algebra is solid. So we're going to add 5/2 to both sides. So over here on the left, I have -2 plus 5/2. And whatever that value is, that's my b value. So let's take a look at this. In order to add fractions, you have to have a common denominator. And a foolproof way of getting a common denominator is to simply multiply by the number 1, but using a version of 1 that uses the denominator of the other fraction. So in this case, we've got the -2 here, and we want to get a denominator of 2. And so we look over here like, oh, denominator is 2. We'll multiply by 2/2. 2/2 is 1. And so -2 times 1 would still be -2. We're just going to change that into an equivalent fraction. So now we have -4/2 plus 5/2, which would give us 1/2. And so our b value is 1/2. So writing the equation for the line, we now give back the 5 and the -2, and we have y equals -1/2 x plus 1/2. So that's one that has some yucky numbers to it. Here are your options. You can also use decimals for some problems. So in this one, if you really, really wanted to, you could take that -5/2 and you could use -2.5. And that would work. And so you would end up with your y-intercept in a decimal form, 0.5. Just be a little bit careful. That's not always possible. Not every fraction has a nice decimal. And then you end up rounding where you don't want to round. You can also use a calculator that handles fractions, and how readily accessible that is depends on what class you're in, what the rules of your teacher are. If you're doing problems like this on a computer program, I know a lot of algebra classes, you do work on the computer and the computer might expect an answer in a certain form and you might not have all the resources. So if you have to do this, do what I did, take a piece of scratch paper, do that fraction work off to the side or use some other resource to get your answer. And remember that the arithmetic and the algebra are two different things, okay? And what I tell my students is, in a pinch, like you write me a note on there that just says, here's what I would do, and I'm just not sure about my fraction arithmetic, so that you're communicating everything that you do know. Now, here's an application problem. These are the fun ones. You are planning a big trip, awesome, and are paying it off in installments. So really big vacations, big trips. You might pay it off in pieces because you just don't have that much money to hand somebody. Every month, you withdraw $200 from your savings account to pay down your balance. After 10 months, you have $15,000 left in your account. And the task here is write an equation to model this using X as time in months and Y is the amount of money in your savings. So you could do this a bunch of different ways, and you could also utilize graphs to be able to do it. But in this particular problem, we are told that after 10 months, you have $15,000 left in your account. So if we're going to do this with the X and the Y, X is going to be your time. So this will be 10, and then Y is the amount of money, and that'll be 15,000. Now I'm not going to go ahead and put the comma in there because I don't want to have 10, 15, 0, like that would be confusing. So we're not going to put the comma in the large number there. Okay, so there's our point. And now we need to know what the slope is. Well, slope is your rate of change. It's how fast is the amount of money in your savings account changing. And if you can remember that definition of slope as the rate of change, then it gives you an idea of what you're looking for when you are looking for your slope. So you're looking for like how fast is the money going down, and that would be this piece of information right here. You withdraw 200 from your account, so your slope would be negative 200. It's negative because you're taking money. Okay, if you were saving money and putting money in, we would use a positive, but the balance is going down. If you were to graph this, okay, you'd have a certain amount of money, and each month you would be losing a certain amount of money, and the amount of money that you would be losing would be the $200. So that should give us what we need. So we have y equals mx plus b. Our y value is 15,000. Our m is negative 200 times our x value, which is 10. Negative 200 times 10 is negative 2,000. And we will solve that for b by adding 2,000 to both sides. So we'll get $17,000. Negative 2,000 plus 2,000 is 0. And that gives us the b value. So the equation here is y equals negative 200x plus 17,000. And again, one of the advantages of doing this is it does give us some key information. So we do have the slope, but we also have the y-intercept, which is $17,000, which would be where we are at time equals 0. Okay, because that's the point that would be on the y-axis, and that would tell us how much money we had in our savings account at the beginning before we started paying off this trip. Now, if those numbers seem kind of big, you're like, ooh, like I don't know if I want to deal with numbers that big, you might see a variation on the directions, and this can often trip students up, so I think this is worth looking at. So the whole first part of that is the same. Every month you would draw 200. 10 months, you have 15,000. Write an equation to model this using x as time in months. Okay, that's the same. And y is the amount of money in your savings in thousands of dollars. And what that means is instead of saying that your point is 10, 15,000, you are simply going to say 10, 15, because now the understanding is that your Y value is in thousands. So you're going to roll that thousands into the number. So it's not $15, it's $15,000. Now, where this might trip you up is when you go to look at the amount you're withdrawing, that also needs to be in thousands of dollars, and it's not. So for that, you might need to take the 200 and divide that by 1,000 to figure out like what you're going to be dealing with, like how many thousands is that? And so that would be 2 over 10 or 0.2 or 2/10. And so your slope in that case would be negative 0.2. Now, when you go to figure this out, now we're going to be using a 15 there. We're going to be using negative 0.2 times 10. Negative 0.2 times 10 is negative 2. And now you're adding 2 to both sides instead of 2,000. If you need to rewind the video, you can look at that. It would have been 2,000. And now we get 17 equals B. So now our equation would be this, negative 0.2x plus 17, with the understanding that the 17 is $17,000. So you will often see that. You'll see that kind of adjustment to the directions. And you want to pay attention to it. It'll sometimes be on a graph that you'll see, or it'll be in the directions of the problem. And it's important to know that, if you do get something wrong, if it's the algebra or if it's something like converting the money into thousands, and that can really empower you to ask better questions to your teacher. Like, I can figure this out if I keep it in regular dollars, but I messed it up when I tried to change it to thousands of dollars. Can we go over that part of the problem? Teachers generally love questions like that because it shows that you did the problem and that you have a very specific piece of it. But that does require that you try the problems and that you are paying attention to the directions. So what does this model tell us? Why would we even be interested in writing that equation? Well, it can tell you the starting amount in your savings account, which is nice in this particular form. It's $17,000. We don't have to do any additional math. That's an advantage to that slope-intercept form. It can tell you how long you can make payments before running out of money. Now, if you were spending $17,000 on a trip, that would, at least at the time of the recording of this video, would be one astronomically large amount of money for a trip. That would be like a long time, and you're going to do all the things and stay in some really great places and eat at some really great restaurants. But you might not have that much to start off with. Let's say you only had $6,000 in your savings account before you started paying this off. How long you can make those payments before you run out of money? That's a really important question, especially if they're taking it directly out of your savings account, and you've got to make sure that there's money there for them to take. How much money you'll have left when you're finished paying off, paying for your trip. So you might be interested in, like, I want to keep $10,000 in my savings account in case I have an emergency expense. Will I still have enough money in that in my savings account after I'm done? Or more realistically, how the constant withdrawals of money will impact your ability to pay other bills that may come in. So a lot of times, like, our bank accounts are not these stagnant things. So you might have a certain amount of money coming out every month to pay for some kind of long-term thing, but you also have a paycheck that's coming in and you have these other bills, and knowing how that particular withdrawal is going to affect your ability to pay other bills, that's really, really relevant. And it does require that you understand how this kind of math works, even if you're not sitting around writing the equations all the time. It's still worth it to practice it, to develop our sense of how the numbers work. All right, so was this video helpful? Please give the video a thumbs up if it was. If I covered something that you had found confusing before or clarified something for you, comment, let me know what you thought, or if you have questions. So if something I did raised more questions for you, and subscribe to the channel for more math help. I will see you in the next video.